Hi, my name's Dan, and this video is one in a series of videos that I'm doing exploring the various logic gates that are available for digital electronics. And in this one, I'm going to look at a gate called the XNOR gate. So to understand this, you probably should have some understanding of Boolean logic and Boolean algebra. That would be helpful. And you should have some understanding of the principles of logic gates, kind of what they are, and you don't need to understand the underlying electronics of how they work, but the idea of what a gate is could be useful for you. As it happens, that I've got a series of videos on Boolean logic and Boolean algebra, which you can check out if you want. And the first one in this particular series does exactly what it says here, which is gives the principles of logic gates. So go check out those if you want to. So anyway, we're going to have a look at the XNOR gate. So what is this? The previous video in this series described XOR, and XOR is effectively exclusive OR. The symbol for that is sometimes this little hat, if you look at the bottom row. And so the example that I gave for exclusive OR is when you're buying an ice cream, you want a cone or a tub. You don't want both, and you don't want neither. And an XNOR is basically the same as an XOR, except the output from that is has had not applied to it, so it's been inverted. So an XNOR is like the Boolean algebra shown on the bottom line here, not a XOR B. And I guess a practical example I could give for that would be shoes, which is I might walk about the house in my shoes if I've just come in. I might have my left shoe on and my right shoe on. I might walk around without my shoes, my left shoe off and my right shoe off. So I would say that both situations where the left shoe is on and the right shoe is on is a valid output, and where neither of them on is a valid output. But I tend not to walk around with just one of them on. So let's have a look at the truth table for that, which, if you know the XOR truth table, this is the inverted output for that. So if one and only one of input A and B is 1, then the output is 0. But if either both of them are 0, then the output's 1. Or if both of them are 1, then the output's 1 as well. And I should say that input A and B are independent of each other, and the gate is symmetrical, like all of the logic gates. You could change those two around and it'd have no difference, but they are discrete from each other. Okay, so let's have a quick look at this in the digital simulation software that I'm using for this, which is called DigitalWorks. Just zooming in there. And so in this software, we've got a couple of inputs here. White means 0 and red means 1. And we've got a signal at the output indicating what's coming out from the gate. So the gate looks like, well, it looks like a combination of an XOR with a NOT bubble. And if you've seen the other videos in the series, if you're following on in order, then you'll know that this little round thing at the output indicates that the output from whatever is behind it has been inverted. And the XOR gate is like the OR gates. It's got a curvy back end, but it's got an extra line in it, so it's got an extra curvy bottom. There we go. So let's demonstrate this working. We've got both inputs are 0. We've got an output of 1. If one and only one of the inputs is 1, then our output goes to 0. Just flick that off and then flick that off on there. But if both of them are on, then the output is on as well. Okay, so that's it from me for now.